This is a B-61 bomb, a lightweight two-stage thermonuclear weapon with 4 delivery options. It is one of our newest and most sophisticated weapons. Design, production, and delivery of these weapons to the military is a job of the Atomic Energy Commission. Only a few years ago, a single weapon design could not have offered the 61's versatility and compact size. However, our nuclear ordnance technology has moved a long way down the road since 1952. For example, when production of the Mark V bomb was a significant step forward. This was the first weapon with a device for automatic in-flight insertion of nuclear components, and was our first missile warhead. At 3,000 pounds, it reflected important design advancements at the time. Or the now obsolete Mark 17, which was retired in 1957. This monster, the first thermonuclear weapon to be stockpiled from a regular production program, was almost 25 feet long and 5 feet in diameter. It weighed more than 42,000 pounds. Nuclear weapons today contrast sharply with those obsolete devices. More sophisticated military needs, coupled with greater versatility in delivery systems and the advancing state-of-the-art, have helped to bring this about. The effects are far-reaching. This is the story of the B-61, the story of a nuclear weapon from concept to stockpile.
But first, before we get into the new bomb, what is a nuclear weapon and how does it work?
A nuclear explosion results from the conversion of mass into energy in nuclear materials. Weight for weight, the energy is millions of times as great as that in a chemical explosion. 2 kinds of nuclear reactions can release large amounts of energy in a short time. They are called fission and fusion. A weapon which derives energy from both of these reactions has 2 major nuclear components, named primary and secondary. The primary is a fission bomb. It derives its energy from the fissioning of uranium and/or plutonium. The primary consists of a hollow sphere of high explosive surrounding a hollow sphere of nuclear materials, known as a pit. When the high explosive is detonated and the nuclear materials are squeezed and compressed to form a supercritical mass, fissioning occurs, creating a nuclear explosion. To accomplish this spherical squeeze and compression, the implosion, as this is called, must be uniformly spherical. This requires uniform or simultaneous detonation of its surface. A weapon which employs both fission and fusion processes through the primary and the secondary can produce an explosion of great power. Surrounding this nuclear system is the ballistic case, which also contains the hardware that makes it possible to deliver and detonate the weapon. This hardware may include the radar, fusing and firing components, the neutron generator that triggers the chain reaction, a tritium source to boost the primary's energy yield, safety devices, cables, and other parts of the electrical system, and a parachute to slow down the speed of the weapon during delivery. The ballistic case may be designed to house a nuclear warhead for use on a missile, or it may be a bomb, such as the B-61. The need for the B-61 weapon system originated with the Air Force. At the time, the military was placing considerable emphasis on fighter-type aircraft that could operate from small airfields and high-speed planes from which lay-down weapons could be delivered at treetop level. One idea was that if a pilot were forced to abort his main mission, he could change the delivery option while in flight, for example, from lay-down to free-fall airburst. This would permit delivery on an alternate target without returning to base. About this time, the Navy also saw possible uses for such an aircraft-carried weapon. Military operational requirements laid on for the system were impressive.
4 in-flight or ground-selectable fusing options: free-fall air burst, free-fall ground burst, retarded air burst, and delayed ground burst or laydown.
Lightweight and no longer than 150 inches, 12.5 feet. Maximum diameter, 15 inches.
Delivery possible at all altitudes from 70,000 feet to 50 feet above the terrain at maximum air speeds.
Low altitude, high-speed delivery with high accuracy and safe escape.
Invulnerability to many adverse environments during storage, transportation, and operational use. Rugged, reliable, simple in design. Easy and safe to maintain, inspect, handle, transport, and store. Its design must minimize the possibility and effects of human error. And the weapon would need no field maintenance or inspection during storage.
Emphasis was placed on the need for high proven reliability with maximum safety against a nuclear accident. A nuclear weapon comes into being and is eventually retired through 7 phases: concept, feasibility study, development engineering, production engineering, first production, quantity production and stockpile, and retirement. Participating during studies of the B-61 were various Washington organizations, Field Command of the Defense Atomic Support Agency, and the AEC's weapons laboratories, Los Alamos Scientific Laboratory, Lawrence Radiation Laboratory at Livermore, and Sandia Laboratory. The Commission's Assistant General Manager for Military Application assigned the design responsibility for the bomb to Los Alamos and Sandia. For another weapon system, the design could just as well have been assigned to LRL Livermore. The University of California operates both LRL and LASL, which are competitive in the design of nuclear and high explosive systems. Defense Research and Engineering, through the Military Liaison Committee, then asked the AEC to move ahead with development engineering for the bomb. On the basis of Air Force and Navy requirements, the Defense Atomic Support Agency prepared the list of military characteristics and the stockpile to target sequence associated with the weapon. The 61 bomb then moved into the Commission's development and manufacturing system. With Albuquerque as a field headquarters, the overall AEC weapons development and production complex consists of 14 facilities, test areas, production plants, and laboratories. Now, having the operational and storage requirements, scientists and engineers at Los Alamos and Sandia took over. At Los Alamos, a team of specialists pooled their talents: physicists, high explosive experts, design and production engineers, and started work on the nuclear system. When a new weapon system is designed, the complete action of nuclear and high explosive components is simulated in a computer. The results indicate design expectations. Once the design is selected, studied by computer technology, and found promising, it is developed in real hardware for more study. At this point, the radioactive material is simulated, ordinary uranium or D-38 being substituted for U-235 and lead usually being substituted for plutonium. Actual implosions of a mock-up primary can be studied in many ways, such as a method called the pin technique. An opening is cut into or through the high explosive and pit so that pins can be placed inside. Upon implosion, the pins are electrically shorted and the system's sphericity can be measured. Los Alamos has developed a high-energy X-ray machine called Fermex, which produces such an enormous flux that a single photograph of the implosion can be taken in a very short period of time. Other studies are made, such as propelling assemblies in an air gun to determine the results of impact on the high explosive, or dropping assemblies from a tower. Criticality studies of the nuclear assembly and any new and unusual design requirements are also carefully examined. When the studies using non-nuclear materials were finished, Lazo began a vigorous development test program with actual explosive devices at the Nevada test site, which is managed by the Commission's Nevada Operations Office. The first nuclear test associated with the B-61 was a safety test of the primary. Later, Los Alamos carried out additional nuclear tests connected with development and safety of the bomb. Working closely with Los Alamos, Sandia Laboratory, the Commission's only ordnance engineering organization, simultaneously was doing design work for the system's non-nuclear components. Sandia designs, develops, and monitors the production of all non-nuclear parts and systems, and packages the whole thing into a weapon which meets such requirements as size, weight, shape, and aerodynamic performance. This is described as weaponizing a device. To do this job, Sandia Corporation operates laboratories in Albuquerque, Livermore, and the Tonopah Test Range in Nevada. Because the 61 would be a laydown weapon, the big problem was slowing down the bomb so that it would survive impact against a thick concrete surface at 165 miles per hour and detonate 31 seconds after release. A ribbon-type parachute, 17 feet in diameter, was designed by the Air Force to retard the bomb. The chute is deployed by a gas generator to line stretch in about 1/10 of a second. All of the Sandia design parts were tested at laboratory facilities. Meanwhile, manufacturing development got underway, and AEC Albuquerque assigned production responsibility for each component to a prime contractor. Los Alamos and Sandia later released the design of each part. As the weapon moved into first production, each of the integrated contractors in the manufacturing complex knew what he was responsible for, the parts he would build or buy, and the assembly work he would perform. The Albuquerque Operations Office sent these assignments, along with other delivery schedule information, to all production contractors. As sources for the nuclear materials, plutonium is supplied from reactors operated by the Richland and Savannah River Operations Offices, and enriched uranium comes from gaseous diffusion plants at Oak Ridge, Paducah, and Portsmouth. The nuclear pit for the 61 is produced at the Rocky Flats plant, located northwest of Denver and operated by Dow Chemical Company. After inspection, the reservoirs are shipped to Savannah River for filling, and the pit assemblies are sent to the Burlington AEC plant for final assembly of the weapon's primary.
At the Y-12 plant at Oak Ridge, which Union Carbide operates for the Commission's Oak Ridge Operations Office.
The production of weapon components is a major responsibility of Y-12, which is the only Oak Ridge installation that retains its old military code name. For the 61 program, the plant fabricates the center section of the weapon case from a high-strength aluminum extrusion to obtain precise ballistic contours and to provide interchangeability with mating parts. The structure is designed to withstand the extreme shock loads of lay-down impact. Other hardware Y-12 produces for the 61 includes the cover plates and the suspension lugs. For the new bomb, as for other multi-stage weapons, the plant manufactures the parts for and assembles the secondary. Y-12 then installs the secondary with radar cables and plastic parts in the weapon case and ships the sub-assembly to Burlington. Also, from heavy water supplied by the Savannah River plant, Oak Ridge separates deuterium gas for shipment back to Savannah River for use in the bomb. Plutonium and tritium for weapons are produced at the Savannah River plant in South Carolina, operated by DuPont for the Commission's Savannah River Operations Office. Savannah River receives reservoirs for the 61 system from Dow Chemical, fills the containers with tritium and deuterium, and ships them to Burlington for final assembly, or directly to stockpile for periodic replacement of the reservoirs.
Procurement from American industry of thousands of parts represents a major effort in the weapons program.
As an example, Bendix Corporation at the Kansas City, Missouri plant during 1967 purchased more than $28 million worth of materials through more than 5,700 suppliers. The plant is a major procurement center and manufacturing facility which produces electronic, electromechanical, and mechanical devices. For the B-61, Bendix manufactures or procures nearly 3,500 different parts. Among these are the forward section of the weapon case, the after section, the pre-flight case section, and the tail fins, the bomb radar nose, a sub-assembly used for all fusing options, which includes dual-channel radar, 2 impact fuses, cable, and honeycombed energy absorber, and a case with attached radome. These parts are designed and insulated to function during the high-temperature environment associated with external carriage of the weapon on high-performance aircraft. Also the firing set, the pre-flight selection control box, electrical component assembly, and the parachute deployment tube and other parts of the chute system. Bendix builds all the test equipment for the bomb, supplies all cables, ground handling equipment, and some of the trainer configurations of the 61. Honeycomb for weapons used to protect against shock, vibration, and heat are uniquely Bendix Kansas City products. They provide a high strength-to-weight ratio. Printed circuitry is another product with wide uses in weapons manufacturing. Other Kansas City plant activities include industrial plating, electrical assembly, electron beam welding, analyzing and evaluating products in the test laboratory, and the use of tape-controlled machine tools better to meet precise production requirements. Detonators for the 61 system come from Mound Laboratory at Miamisburg, Ohio, near Dayton, which Monsanto Research Corporation operates as a research and development laboratory and production facility. In the weapon field, Mound develops and fabricates components such as exploding bridge wire detonators, ferroelectric transducers, and explosive timers, explosive drivers, and radioactive initiators. In addition to process development and manufacturing, Mound also does research on diagnostic elements, chemical explosives, and other materials used in weapons. For the 61, Mound manufactures the detonators, procures the spin rocket and gas generator, and performs quality and reliability tests on the reservoirs. New weapons require miniaturized parts and precision production. As an example, the soldering of bridge wires for the B-61 detonators is a hand operation performed under a microscope. Inspection and quality control procedures are strict. Large samples of detonators are subjected to thermal and mechanical environments and are test-fired to determine if they will function with the simultaneity required. A sample from each production increment is fired. Electronic monitoring systems and a high-speed rotating mirror camera reveal that the devices will fire. Completed detonators are packed in shipping cases designed to prevent propagation of further explosions if one of the devices ignites. Detonators for the 61 are then shipped to Burlington for final assembly, while others are held at Mound for long-term surveillance. Another important part of the bomb's nuclear system is the neutron generator. Since the early 1950s, General Electric has performed development work on neutron generators for the AEC. GE produces the units for the weapons program at the Pinellas Peninsula plant, located between Clearwater and St. Petersburg, Florida. The device Pinellas supplies for the 61 program is a timed neutron pulse generator about 3 inches in height and weighing some 2.7 pounds. It provides a burst of neutrons at the critical time to start the nuclear system's chain reaction. The generators are complex miniaturized particle accelerators, which produce neutrons by a thermonuclear reaction. Assembly requires a high degree of cleanliness and advanced encapsulation techniques. Most of the parts for the weapon have now been built. Many components have been put together into sub-assemblies, and all of these parts flow to the final assembly point. The Burlington AEC plant, located at the Iowa Ammunition Plant and operated for the AEC by Mason and Hanger Silas Mason Company. Here, all components and sub-assemblies originating at other facilities come together with the components of high explosives to form the complete bomb. In addition to final assembly, Burlington's main mission is fabrication of chemical explosives. A secondary mission is development support of the design agencies. Some assembly work at Burlington is performed in specially designed structures, such as these cells or gravel gerties, where high explosive parts are assembled with nuclear components of plutonium. With ceilings of heavy steel mesh and a thick gravel overlay, the cells are designed to prevent the spread of radioactivity outside the plant site in the event of an accidental detonation. Other assembly work also is done in specially constructed buildings. Each consists of numerous bays of heavy concrete on 3 sides, with one blowout-type wall and roof. Explosive materials handled in each area are limited in quantity. As at other AEC weapons facilities, safety is a way of life at Burlington, and the plant's record with the National Safety Council is proof of this. Both Burlington and the Pantex plant near Amarillo, Texas, the other weapons assembly and high explosive fabrication facility, require extensive shipping programs, with components and assembled weapons being shipped and received by specially designed trucks, rail equipment, and by air. Contractor-operated aircraft and military planes are used. Specially built ATMX cars, such as these shown at Pantex, are escorted by Albuquerque-based couriers who are berthed in a car that accompanies each shipment. The ATMX cars are kept under constant surveillance. Transport of components, sub-assemblies, and completely assembled weapons in AEC custody is an Albuquerque operations responsibility. The record is excellent. Within the AEC, there has never been an accident in a public area involving detonation of chemical explosives within a weapon. In no case of either commission or military custody, of course, has any accident resulted in a nuclear explosion. Assuring the reliability of weapons requires a continuous program. A part of this job is done at the Pantex plant, which performs weapons quality assurance work in addition to fabrication of high explosive components and final assembly. Quality assurance activities at Pantex involve new material system tests, stockpile sampling, and joint firing tests. Sandia employees perform the evaluations. The new material system test program for the B-61 involves testing of assemblies randomly selected from production. The bomb is partially disassembled, and the weapon, with the nuclear and HE components simulated, is placed on a tester, and the entire electrical mechanism is operated. Information is fed into a computer system, which then provides answers as to whether the circuitry operated successfully. The goal here is to determine whether production items meet design intent and specifications, and to provide additional reliability assessment information. Stockpile sampling and other test programs evaluate degradation and field use effects, all a part of the continuing effort to assure the reliability of nuclear weapons, both those going into stockpile and those in the hands of the military for possible operational use. This has been the story of the 61 bomb, one of our newest and most versatile weapons, as told against the background of the Atomic Energy Commission's development and production organization. It is a story of the long and difficult path from a stated military need to a completed weapon system, and the thousands of people involved with their many skills and talents, along with the other resources of our laboratories and American industry.